Alright, we're back. So, we need to implement this provide memory function. Alright, so how long do you think it's going to take to debug this? Do you think it's solid, or do you think we have a million bugs? Or somewhere in between those two. You guys have a little discussion amongst yourselves. How screwed do you think we are once this starts trying to put text into the file? Okay, so that's the end of the usefulness of that golden array as reference. This is where it gets a little tricky. Basically now, alright, so Canoodles is asking for a brief description of code transforms or good search terms. I'm afraid I don't have good search terms because I made it up myself. Or at least I made up my conception of it. I've heard some people use the term transformations of code before, but I don't know if there's any technical, like, conventional meaning for that or anything like this. You know, I'm just sort of extrapolated from that and my understanding of things and came up with a concept. So, basically, code transforms can be thought of as existing in two groups. All code transforms are basically something that happens where you take some code, and this is a bit harder to show here. I can just open this up. I really like this concept, and I've never explained it before, so I'm going to take a quick detour to do this. Okay, so let's implement a insertion sort. So here's an array of integers we want to sort. Here's how long that array is. We're going to insert sort that. Well, one way to look at insert sort is it's um, it's basically taking a number, right? If you have A, B, C, D, E, F, G, and you look at B and you decide whether or not it needs to swap positions with A. Maybe it does, maybe it doesn't, and you perform that operation. Then you look at C and you need to decide, does it need to swap with A, does it need to swap with B? Maybe it needs to swap with A and not B. So you take that and you swap it into there. Then you look at D and you say, okay, it needs to swap with A, it needs to swap with C, etc. Now, a more optimized version doesn't do 2 different swaps to put D here, but we'll get to that, okay? So the basic idea is, starting with an array, start from this one and swap with this one if necessary. So, we'll literally write that. So basically, if size is at least 2, then apply this concept. If items 1 is less than items 0, swap items 1 and 0. Right? And we'll make our swap macro real quick. Swap AB auto temp equals A, B equals B, B equals temp. Right? Okay. So that'll perform that first swap. And then the question becomes, okay, well, what if we have at least 3 items, you know? In that case, we need to look at C, and we need to say, look, if items 2 is less than items 1, we need to perform a swap between them. And then if items 1 is less than items 0, swap them, right? This is the logic I was explaining before. And you'll notice if we didn't do the swap here, then this is just repeating the comparison from up here, which will already have been swapped. So it's a little bit wasteful the way I'm writing it right now. But hopefully you can see that it's still correct. It's just, you know, not great. And the way I'm going to do this just to speed it up is I'll copy that and do it again. And you'll see that now we're saying if we have at least 4, then check 3 and 2, swap them if necessary, check 2 and 1, swap them if necessary, check 1 and 0, swap them if necessary. So this is obviously a pretty poor way to write a sort, because we have to continuously grow this thing longer and longer just to handle 4 we've gotten to this point, and then I have to copy all of this, add another one of these clauses, and then that handles 1 more, and each time I want to handle 1 more, it gets longer. So this is where I actually came up with the idea of code transform. The way I think about it is, if you look at this code, you might say, oh, you know what, I can parameterize it on certain features. First of all, what's inside of each of these ifs looks similar to each next one. It's just that they are in a loop, right? So it's like, here we have 1 0, 2 1 1 0, 3 2 2 1 1 0, right? And so you can see each time it's just getting 1 longer than the previous one. So we could rethink of this as parameterize this here so that this 1 and 0 and this 1 and 0 I basically say take this number, this number, this number, and this number and parameterize them on some variable I. And, you know, we don't need to use we can use declare anywhere for this purpose. So on some variable I, which is equal to 0. So then it comes in here and goes, okay, 1, that's equal to I plus 1, I plus 1, I, and I. Now, how you figure out how it figures out whether that's I plus 1 or I times 2 or etc., because it could be ambiguous, isn't actually well defined. So that's a little bit not how it works when you do automated code transforms, but I'm just showing you the general concept, and then I'll show you ways that you can compute certain transforms next. So that's fine, and the nice thing is now you can go ahead and apply the same logic everywhere. This guy is I1, and then we take this code, and you can see now we'll have a nice situation where each repeated chunk is exactly the same, with the only difference being that we change I at each step. So we've just made it so from going from having a bunch of these 3 lines of code where the 3 lines were different each time to a situation where we still have those 3 lines of code every time, but now the same 3 lines get repeated, right? And once we're in a situation where we've got this, so that's a code transform because it preserves what the code used to do, but now it expresses it in a different way, right? So this preserves exactly what the code used to do, except now we've parameterized some of the constants on this variable I. And if you have a block of code which is the same in multiple places, like this is the same as this is the same as this is the same as this, all of these can be written as loops now. So then the question just becomes, alright, how far does my loop need to go? Well, it needs to go until I is 0. So while I is greater than or equal to 0, and each time I is decreasing by 1, right? You can see down here each time I decreases by 1, so we can capture that way. And then we could even say this goes right here, right? So there we go. Now we can parameterize each of these like infinite expanding things this way. So that starts with an I equals 1. And this one here starts with an I equals 2. Alright, so now we've fixed the problem that we have code that gets longer and longer by like a quadratic amount. Now if I add something, I'm always adding the same amount for each step. I just have to add a 5 there and a 3 there. So that's a lot nicer, but not nice enough to make a general purpose sort that can handle size that goes up to like 100, right? But again, we're in a situation, if we look, where this code is the same as this code is the same as this code is the same as this code. So if we can detect that those codes are all the same and then just identify the differences, we can parameterize on something else. In this case, we can see that we have 2, 0, 3, 1, 4, 2, 5, 3. And if we keep going, the rule is whatever number we have here, subtract 2 and put it there. And after each step, add 1. So if we say that we have like this number that's 0, 1, 2, and 3 that's increasing, right, we'll call it j equals 0. And instead of putting zeros here, everywhere where we need that parameter, we'll put j, j, j. And so now I've parameterized the same piece of code on this j variable. And I've preserved the behavior again by making sure j is always equal to what the constant used to be. And then we can also say this right here, these constants are also floating around and not doing us any good. Let's say that they are j plus 2. Right? So that's nice. And then we can see that we're all set up for a loop because we have literally the same code repeated now. It's the same exact code, with the only difference being that j, which we run it on, is different each time. So what we have here is a loop that starts at 0 and that continues increasing for as long as this is true. J size is greater than or equal to j plus 2. So what we really want is put that into j inside the beginning of the loop. While this is still true, increment our j. And bada boom, right? Insert sort. So just like that, the process was like, look at some code, find ways where you can parameterize that code, and the reverse of that is also sometimes you might look at this and say, you know what, my array is always 5 long, so I want to take this code here and I want to say that size, which we've parameterized on, let's bake into that the number 5. So it'll put a 5 here and a 5 here. And then it can also have the option of saying, hey, since we have a loop here that's got it's based on a constant step, we can expand the loop out and get rid of the loop itself. So we'll repeat the code the 5 times that we need and it's done, right? And so on. We can do all sorts of stuff like that. But now that it's in this form, it's this insert sort, but we're still doing this thing where like we keep on swapping even when we don't, and we can sort of look at places where we can take advantage of stuff. And that's the idea of a code transform, is looking at code and finding ways to maintain what it does while uh, changing its form, basically. And that's one way to look at code transforms. The other thing a code transform can do, it's not really a code transform so much as just editing the abstract syntax tree. That's like a different concept that's also going to happen. Um, trying to think if there's any other good examples. Like that's basically it. That's basically what a code transform is, according to me. But that's an example of doing code transforms on something that is pretty straightforward in terms of its code that runs. Other stuff then is also code transforms, and you have like your stuff here, and you've named your stuff, and then you've got like your thing, and that's like right here, and you go, you know what, thing is kind of obsolete. It's got like, it's XYZ in it and everything, but it's sort of obsolete now because the only person who has a thing in my whole program is stuff. Nobody uses pointers to things or anything, right? So what you could do is say, first of all, do a check. Can I just inline this struct here? And if so, do so, right? And alternatively, you might say you have this XYZ and say, you know what, I want to put that into a struct, and it'll make all the changes to make that a struct, etc. There's all sorts of code transforms you can do where you say, I want to take this existing code and parameterize it or regroup it or inline it, etc. That transforms it without changing what it essentially means, or what it essentially will do, especially. Anyway, that's all I mean by a code transform. Let me look at some stuff now. So, are we ready to do edits, or was I was still implementing provide memory, right? Okay, so what I need to do now is, when I get new memory, basically that new chunk of memory has some portion of it that needs to be initialized into the free list. Why do I not do... K-Nucleus is asking why I don't do this. I don't know, there's definitely something I don't like about it, but it's just a feeling. For one thing, I like seeing my name in lowercase because you don't usually see it, but also capitals sort of draw attention to things in code. Like a capital, I usually use it to denote this is this type of thing versus this is that type of thing. So like an all caps thing is like, hey, you really should like pay attention. If you're looking for me, I'm right here, pay attention. A single capital by itself normally means I'm this, you know, I'm this special type of name that's usually associated with just with, types, and then all of these things here are like instances, whether you have a function name or a uh, member or a constant or whatever, they're all just little names. Now, obviously, Casey has a different naming scheme, so this same line of reasoning wouldn't apply to him necessarily, but basically the point is a capital draws attention to something, and the name here isn't that important. It's more like if you're here, what you should really read is over here, and a capital here makes this more important than this. And I also write these in lowercase without sentences. So like if I were to do this everywhere, then it looks like it's very important that I was the person who did it to me. And I don't really like that. It just sort of strikes me in a certain way. I don't have a particularly salient reason besides just the way it looks when I try to read around the code around it. Also, there's something about it's really easy to type note parenthesis, but then A is on my pinky finger. This is actually a valid reason, actually. If I do note parenthesis, I can hold my pinky finger on the left shift the whole time to do that, but then to hit the A capital, I have to switch to pinky finger right hand shift A to do that. And I'll bet you, yeah, the C in Casey is not that easy to reach either. It's a little easier than the A for sure, because you don't need to use the pinky. But I bet if I had like a name like Jack, oops, let me try that again. It wouldn't, yeah, because then it doesn't really matter. If I can get my finger back to the right place. Even then, trying to get that A in there is a little tricky. I can't type Jack for some reason. It's like a tricky name to type. Anyway, enough drills. Back to the code. Let's see, the mem copy right there. I need to figure out how many new things I need to initialize. And if I'm growing string memory, that means I need to look at the new max. I don't like that name here. That'll just be size. Size minus the old stuff. More like here divided by rope string full size gives you the new count. And if you start from I equals Okay, last one from Canuckles. He says it's probably because OOP starts affecting me a little because I've been doing Sharp the last 2 months and almost no C. Programs are essentially one giant beautiful logic file of variables and funcs, which include yeah, I mean, a C program is just functions and structs, basically, and some public global variables, and then includes, which include more of those things, again. Yeah, that's all you have. There is something sort of aesthetically pleasing about just having those. Those few things. Does the mem copy, figures out where it's going to iterate the new data, plus I. Rope string next free equals I plus rope string full size. So each one figures out the next one. We want all except for the last one actually, so the new count buffer string count equals this new count. Buffer data equals the new data. String count equals the new count. Multiply the new count up. But not before you subtract 1. Right? Going along, and then the very last one, the next free is 0. Oh wait, no, the next free should be buffer free string, come on. Free rope string, and then the buffer's free rope string should equal that initial value of I. Buffer string, which we don't really have sitting around anymore. The new count, no. minus 1 times all of that. Rope string equals wherever we are now, equals free rope string, and this equals start. There we go. So all of the new data just plops right in and becomes a part of the free list, just like that. And same basic idea has got to happen down here. Buffer nodes equals the rope node pointer to new data. Start equals node count and equals the size of a rope node. Node count equals that end variable and equals end minus 1. I equals start, I is less than end, plus plus I. Rope, I need a plus plus node. I need a rope node. Node equals buffer nodes plus start. Node parent equals I plus 1. Bada boom. Gotten pretty close. Not done though, because node parent the last must equal buffer free rope node, and the buffer free rope node must equal the start position. Now, where are these warnings coming from, huh? Potentially uninitialized variable right. You're right. Oh, damn. Okay, so all of these, so I have an error in my logic. All of these variables, end, throwaway, right, where does start come from? Okay, that's fine. So no, these variables here, left, right, throwaway, and middle, all need... Okay, so this is where you would want to code transform, right? This is a perfect time for them, because this, what I want to do is say, those belong in a, technically those belong inside this. These should be provided by this, is what I would want to specify, right? I have a struct pointer already coming in. I want to say, basically, it goes like this. Left equals buffer edit state left. Right, throwaway, middle. Right, throw away, middle. And then anytime I have to get out, here's Canuckles, you there? I have a lesson for you. You asked earlier why I don't want to have returns in the middle of the function. Well, because as often does turn out, there's something that I want to do anytime the function ends. And now I don't have to write that in 5 places. You see that? Those 4 things there that I just had to write. I would have had to put them in all 5 of the places there, as well as these other 5 places if I had put the returns everywhere. But with the go-tos, now I've just got to put it in once. And it's just like, it always works out nicer to have one return in your whole function. That should cause an error. Buffer edit state. Yep, well, it happened. I didn't even see it coming that time. I thought maybe you'd found a spot where it looked pretty silly for me to do what I was doing, but it happened anyway. Now the thing what I really want to do is have a code transform, but I don't. Rope buffer edit stage state equals buffer edit state equals state clears out to 0, and then state dot needs to be pasted all over the place. State dot 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 done. Okay, cool. The ropes weren't as hard as the multi-gap buffer, but they were definitely more code. Or at least I'm pretty sure they were more code. Guess I should check that before I claim it. Yeah, they were about 200 lines longer, and I haven't even gotten this in there yet, which will add in another couple tens of lines. Looks like about 20 lines, maybe 15. Okay. So now we can finally see the 1,000,001 errors that I have created today. Okay. Let me try to insert the letter A. It's frozen, so let's see what we got on our hands here. Node equals, if nodes plus node left equals child. Well, how could it? Child's not being updated. What is this? What is this? Who wrote this? Child equals the node we're at. The node equals that child's parent. Put that inside the loop. Yup. go. A. Aha! Debug check failed. Interesting. Glad that I did the extra work to assert for that one. Request amount. Wait a minute. Wait a minute. Wait a minute. Alright, so the hope was that this code would do a sort of a thing where uh, 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 this loop here and this loop here are identical, with the exception that this one is checking on the right hand side and this one is checking on the left hand side. I just saw that. So that's how good I'm doing today. That's how well I'm handling this code. Anyway. Split root equals 0. It does not. So it does the but shouldn't it be right? Alright, so I want to put a little breakpointy here and see it happen next time. Insert an A, what happens? So it's come along to here. It's come to this, has it? Split root. Let me take a look at the buffer and see what we've got going on. So the buffer, the node count is 2048. So that is cool, and it's looking at that that concept of doing a concatenation. So we are storing a split root there. Do we have any free rope nodes? We do. Node 11 is free. That is interesting. That is very interesting. And it's saying, okay, I'm going to do a concat. Alright, what does that involve? If we allocate, okay, that's good. We've allocated a rope node. It's 11. And we're just concatenating them together. 11 is the node that these guys are stored underneath. Oh, that god damn. So this assert failed, and then like it went into a callback, and no. It was trying to render this whole thing. Why does it do this? So yeah, this assert triggered a callback in Windows that ruins the whole stack, and like the whole thing is fucked. And what are you supposed to do? Because it's not like I can actually see what it was trying to render. Okay, so the debug check is coming out 0, even though it didn't actually fail to allocate what it needed. So let's take a look at that. A F11 result equals 0. So actually I want to assert, I'm just asserting the wrong thing. is the problem there. I should assert that that is not true, because that's how I want it to behave now that I look at it. But I'm not asserting the right way. I'm asserting that that should be true, and I should actually assert that should be false. 744. There we go. Right prev equals left. I don't know what that would mean. Who are you talking to? Oh, we have a general memory allocation bug on our hands again. So it's trying to do a merge and it doesn't make any sense. View replace range. Which means we have memory corruption, in case it's not clear to anyone. Replace range. Do single edit. General memory free. Okay, so it went into the replace range function, decided it needed to do a memory request, got some new data, and that went fine, but then when it went to free some other data, things went haywire. So I'm going to put a breakpoint there, and we'll catch it before it happens next time. Hey, I can actually see some of the stuff that it drew this time, which is interesting. But it did several requests before there was a problem, which was kind of surprising. I was mostly surprised that it did several requests at all. It seems like it shouldn't be doing so many requests for memory. So I'm gonna walk through this slowly and watch what happens. Something deeper is going on here than just memory corruption. It's like maybe we're trying to allocate memory when we too often, maybe, which might be a problem. All the time allocating. We'll walk through and find out. So it says I'm getting ready to replace a range in this rope buffer, and it comes through and its edit stage is 0 and its states are all zeroed and it's all ready to go. It says here's the shift amount on this puppy. It's 1. He goes, okay, no problems yet. Edit stage less than 0. Case. Alright, so we want to do a buffer split. So far no problems here. What's the node index if I try to find this node? It's node 11 that we're going to split off. Okay. Node. So we're doing a split off of a node 11. And the start position is less than the position of the spot where we're writing, so we're going to do a string split. Okay. String split in activate. Position is greater than 0. Allocate the rope string. That fails. So it says we're going to need some memory. We're going to grow some strings. We're going to need a lot. Okay. So he says result is 1. Oh, we need to go to the end, return that 1. He goes, aha, we have an issue, so edit stage is staying at 0 and everything. Throw away. Right, they're not affected at all. The state is still all zeros, and we return a result of 1. And he goes, okay, he needs some memory. So, here's the deal. How much does he need? Alright, he's got it. Here's the new memory. Provide that to him. Let's see what happens. So he says, okay, we got to grow the string memory. And let's see, the size of that's big enough. Here's the old thing we're not going to need anymore. Let's put the new stuff in right there. And then set the buffer data. That's going to take a while, so I'll skip to the end of it. And it says, here's the final rope string in that list. It should know that its next free is -1. There's not any more free strings after that. And this new free rope string can go to here, 131072. Okay. Do we have some old data? Oh, yep, we do. We go to free it. Everything kind of just goes fine with that, and it's good. Onwards. So we start with the state again. The edit stage is still less than 5, so we still have work to do. I never reduce that edit stage back to 0 when we're done, so that's a problem right there, but ignoring that, let's try to do the split again. And it goes, aha, we need to do a string split. Comes through and it's like, aha, we've got string space now. Wait, thank you for getting me that memory so that I can get this far. Let me allocate a rope node. Oh, can't do that, so result, free that string space again. We're not growing string memory, and the amount we want now is all of this. Yep, we need more memory. Done. Okay, he goes, okay, we need more memory. So edit state's not updated yet. He comes in, allocates, provides the memory. Okay. Knowing that, we copy all of the nodes right there into there. We say, here's the new nodes. Buffer count start equals node count. And equals 2048. Good. If we go one less than that, start from the beginning. 56. No. Okay. I equals 124, 10, 47. And each time through it sets up next, next. And just to make sure, a quick sanity check. I believe that is correct, but you know what? We have more code here than we deserve to have, so maybe this isn't so much longer than the multi-gap buffer after all. We'll find out soon. But anyway, parent wait, left wait, buffer. We don't really need comments anymore. Okay, that's working. Whoa. Oh. Okay. Made a mistake there when I edited the code. So here we are. Alright, so first time through is okay. The second time through is okay. Here we go, third time through. What are we providing here? Why do we even need more memory at this point? We need more than what we had? Oh boy, okay. So we supply more memory. What's the new count going to be now? Oh, there's a problem. So yeah, there's some sort of bug where it's requesting memory even though it's requesting the same amount of memory again. I'll have to track that down soon. I'll be right back. Oops. I had my mic muted for a bit there, but now it's okay. You can hear me again. So, what I was saying was, what's going on with this code? What the fuck? This is crazy. But now it's starting to work out, and you can hear me again, so it should be better now. Whoops. And let's see, we grab the child. The node is the nodes plus the parent. Child break. Okay. The split root is 0. The split root equals the right hand side. Okay, good. So right there what just happened was we decided that the root of this thing is currently the right hand side of the thing we got, which is a single node floating over there. That's fine. That's what we wanted. That's what we wanted. So it's good. Then what we need to do is say, okay, what's the node index of the node we're on now? It's 11. That's the parent. It has no right to child because we've just split it off. Node equals nodes, node left. Go down to the left side and then reduce this node. Okay, so now we're reducing node 11. And when it gets that pointer to that node, it's going to see that it has a left child to 1024 and a right child to 0 and a parent to 9. And it's going to say, okay, let's grab that parent who has a left child of 10 and a right child of 11. And let's grab that child index. And that child index, is it this one? No, yes. Yes, that is the one. It's not 0. The child pointer, we've got that. So then we take the parent left. Does that equal the node index? No, it doesn't. So parent right becomes this. Parent right becomes 1024. And then the child's parent becomes the node's parent, which is 9. Okay, so now we've just linked up that reducible node so that it's out and like its parent and its child know of each other and talk to each other directly, and he's just out of the loop now. And the parent, while parent does not equal nodes, the base, the super root, look at that parent's weight and set it to all of this stuff. So yeah, that actually changed, so it's a good thing we went through and recomputed. Take the left weight, which has not changed, and update parent to the next one. Are we done? No. Update weight, yes. Update left weight, yes. Nodes plus parent. Are we done? No. Update the weight. Update the left weight. Update parent. Are we done? No. Update the weight. Update the left weight. Update nodes. Wait, the parent. Are we done? No. Are we done? Still no. The weight's getting pretty big though, so we must be getting close. Still not done yet. Okay. Oh. Keep going. 10. Yep. Yep. And there we go. Oh yeah, you can't see the values that I see when I hover, can you? Because it's like Visual Studio and OBS both blowing as hard as possible, and so they can't figure out how to show you exactly what I see for some reason. Well, I assure you, it was all, it all made sense. It all added up. And the new weight and the left weight get updated. Okay. And we free the rope node at 11. Okay, so that should lead to this node here, which, let's see, Canuckles, that's not too hard to deal with. Canuckles is asking about how to prevent a program from hogging an entire core and just spinning as fast as possible. If you have an application like this, uh, it just has like a frame rate. You know, like it does some computation and waits for a certain period of time until it needs to do another computation, and so on. It's just a frame rate limiter like a game would have. It's not like as slick as a game probably has because I don't care about hitting the frame rate all the time. But especially for the purpose of like having fades and scrolls and stuff that are animated, it's all very much just a frame rate like system where you get a frame and then you have a certain period of time and then you have the next frame, and anytime, as long as you can compute everything you need to within one frame, you're good. Now there is a certain time when it spins up a core and just burns that core as hard as it can, and that's whenever it launches a background job. And what I could do is say that I like have it run at half speed or something by sleeping off, you know, portions of time that are like half of a frame, so it takes twice as many frames to get done. Now, what most editors would do, like what a typical, if you ask someone what to do there, they would say you shouldn't. That should never be a problem because you should be waiting on input. Then that input triggers a change. Like you have like the Windows loop, and it's waiting for a message, and then once it gets a message, it updates the state, and then it waits for the next message. And while there's no messages, nothing happens. But if you do that, you can't have animations and stuff very easily. You have to like do crazy stuff where you like make sure you get messages frequently enough on a certain schedule to update the frame, like the position of all the animations, and it's bleh. It's much easier for me, at least, to just treat it kind of like a game. And what I do, one optimization I have is I don't render every frame. I only render when an optimization is, or when an animation is running and stuff. Yeah, I could do a thing where if it's ever in the middle of an animation, it then notifies the system that you need a perpetual frame, like you need to keep getting updates even if there's not messages. But that seems like more complicated than just basically if nothing has to be done during a frame, the time that it takes to do like a frame rate's a very easy thing to implement. I don't think there's a huge cost to like every once in like every 30 times per second failing like 5 ifs, right? There's basically, if nothing needs to be done, it'll go through 5 ifs or 10 ifs or something and go no 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 no, and then sleep for another 30th of a second. Like that's very very low power usage. Like that's like nothing, right? So it really is only doing stuff when it needs to. It's just I don't ever rely on Windows to tell me when stuff needs to be done. Okay, so we got to this edit stage. Ooh, I left this code in. Well, doesn't matter. I understand that that's a way to limit CPU usage, but like, it already uses 0 CPU if you don't do anything. If I haven't been clear, like, it's not using any CPU anyway. Because it doesn't like have to redraw anything, it doesn't have to compute anything, it just does a couple of ifs and then goes back to sleep. And it makes my life a lot easier to like code everything. Alright, let's see what this one comes up with. Okay. Bicanicals, start, end, they're both the same. Alright, so what I actually need to do here, I should go back and be a little bit more clever than what I was being. Because there's a small issue here, so I'm going to take out everything that has to do with the switch in the loop for now. Okay, so this is basically like, hey, if I come down here, if start equals end, we're going to do something unusual, otherwise do the second split. If the start equals end, then just do state.left equals state.throwaway. Right, that way we don't do a second split when really we just need to one split. And build tree will work the same way. Okay, and then why do we have two concats? We have two concats because there's a left side, a right side, and a middle side. So a left side, a right side, and a middle side. So basically, if len is greater than 0, we actually do this work. Otherwise, we need to do just one thing. Concat left and right directly together, storing the result in the middle. Okay, so that's some nice optimizations. The only trick now is that we have more states to deal with, right? So 1, 2, 3, 4, 5 instead of 4, and they're a little complicated because they got control flow more than they used to, but that's okay. We will make it work. So buffer edit stage plus the buffer edit stage. Do that for each step of the stage, and while that's less than 6. And then here we'll have a case 0, break. Right here we'll have a case 1. Oh, I need to add in the switch. Switch on the edit stage. Boom. Case 1. Break. Case 2. So now, while it's going along, if it sees that length is equal to 0, yeah, so this will be kind of fun. If the length is greater than 0, then edit, we'll say if length is greater than 0, then buffer edit stage equals 2, so that's like does nothing. Otherwise, buffer edit stage 3, 4, 5, 6, so 5. Right? So that's kind of like having a branch inside of our states. Case 2, case 3, case 4, and really what I want to say here is if length equals 0, edit stage equals 5, otherwise nothing happens at all. Right? Case 4, case 5, break, and technically I don't even need a separate state for that so much as I just put it right here, don't I? So if length equals 0, 2, 3, 4, case 5. Right? So you go to 4, you up there while you're less than 6, sure. And if we ever get done, then the edit stage equals 0, so that it's back to the beginning the next time through. And this right here just sort of acts as like branching, so that if we are here and we go do that edit stage, okay. I want to see if we're still breaking first. Okay, we are. And it's happening when buffer goes when the bubble goes all crazy. So there's still a problem in the general memory. Most likely a corruption situation. So we'll keep looking through this carefully. Okay, in we come in here. We realize we can't allocate the row or the string, so we ask for more string memory. And out we come. Can I have string memory? Everything works. We come back through and edit stage is still 0, so it tries again to split the right hand side away. Fails again. This time it needs node memory, so it comes through again. We provide node memory and free the old nodes. Alright, this time we come through, and when we do the string split, we finally get all the nodes we need and all the string we need, and then we get out just okay. Nice. So then we set up the split root situation. We end up doing a bunch of work, and when we're done, we have two little trees floating around, which make up node A and node B, and that's the split. That came away without failing, so now we go on to stage 1. In this case, start does equal end, so we set left to throw away, and len does not equal 0, so we go on to stage 2. Here, it builds a floating tree. Let's see how that goes. Allocates a rope node. That works out fine. Okay. Ooh. I skipped that accidentally. It failed to build the tree, so I want to rerun this again and figure out why. It should have plenty of memory for that, so there's not really a good reason for that to happen. So I'm going to look into it. So it comes in here to build the tree. Uh-oh. Uh-oh. Sounds like the dog was getting into trouble. Anyway, here it is. Okay. So, right, result equals 0. What does this thing do? If it returns 1, if it returns 0, bad. If buffer build tree. I believe buffer build tree is set up so that when it returns 1, that's the opposite of what I think it should be. And I should go flip that because I've made a mistake twice now based on that. So, buffer build tree. Oops, sorry. About flicking the mic for you guys. Build tree. Where do I debug check? Was that something else? Yeah, it was. Okay. A. Let's see. First time through, fine. Second time through, fine. Third time through, we get to here. And this thing says, look, result is 1. We're on our way to getting out okay. It allocates this rope node just fine. It allocates its rope string just fine. And, you know, it's done. And this continues until, oh, result equals 1. Okay, so I think I need to swap result here to if not result. Yeah, so 276. There we go. A. F5, F5, F5. We get to here. This thing runs through. It's only got to build a tiny little tree. It just ends up pushing like one single leaf node onto that tree. There you go. It's done. It did not fail at any point. So it sets the out. It sets the free rope node. And, okay, so the reason we were getting multiple requests for the same size before was because it was saying it needed memory when it didn't, and it was just reusing the same size it had. Like, it was reusing the same state for updating memory that it already had, but it wasn't really needing to update memory, so it was just repeating that unnecessarily. So step 2, success. Step 3, we gotta do a concat, success. Step 4, we gotta do another concat, success. Step 5. Oh, so right there we need to do so case 799. Buffer edit stage equals 5. So that we're all done. Or I can say 6, right? You set it to 6 and you're just done. You're out. A. F5. Doot, 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 doot. Doot, 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 doot. Doot, 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 doot. Edit stage is 0. Fails again. Edit stage is still 0. Succeeds. Comes through here. Edit stage is 1. Succeeds. Comes through. Edit stage is 2. Comes through. Succeeds. Edit stage is 3. Comes through. Succeeds. Edit stage is 4. Comes through. Succeeds. Skips to the end. Breaks the loop. Sets the edit stage to 0. Updates everything. Reinitializes edit state back to 0. And end of loop. Okay. So that was kind of like it finished. Is that a problem? Yes! Okay. I think that that's it for me today, or at least for the stream for now. I might do more work later, but I think I've had enough streaming today, and we've got characters showing up when I type them. So that's pretty good. Now, of course, the problem is I'm not merging anything in a smart way, so this is getting really gross really fast, and there's probably plenty of bugs to find still. I haven't done any stress testing yet, so there's still plenty to come on the ropes, possibly another day or two. Maybe just tomorrow if I put a bunch of time on this in tonight. But anyway, I'm pretty happy with that result, and I think now's a good time to end the stream for today. Thanks to everybody who came out, and I'll see you guys around. Bye.